This is Dr. Selby here, and I want to discuss electronic transitions using the Bohr model. Let's start off with key points of the Bohr model of a hydrogen atom. So, the first key point is that electron energy levels are quantized. So, here I am showing kind of a depiction of an H atom. And in its lowest energy state, we're going to have an electron in that n equals 1 level. And electrons can reside only in certain levels. So they can reside in n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, n equals 7. No, they don't stop at 4. In fact, the n values do approach affinity. And what those n values have in common is whenever you're in n equals 1, you're the same distance from the nucleus. Whenever you're in n equals 2, you're the same distance from the nucleus. So that's a key point. They're quantized. You can't be at, there's no n equals half or n equals 1.2. It doesn't, these are integers, and you can only be in one of these levels, integer levels. Next key point, which I kind of touched on already, is an electron in the n equals 1 level is the lowest energy level possible. So, and we call that the ground state. But so here, this is an n equals 1. We could say electron here is n equals 1. That's the lowest energy level. And it's the closest to the nucleus, which you can tell from this figure here. Here's the nucleus. And that's closer than if it was, say, in n equals 2, which would be further away. And then a next point is the strength of attraction between the electron and the nucleus is strongest when it's closer to the nucleus. So the further it gets away, the higher the energy. So distance, you shorten the distance between that electron and the proton in the nucleus, and the energy is stronger. It's more attracted. As you increase it, the energy increases, the potential energy increases, and it's less attracted. So that actually covered that point too. And the last point I want to come to is that the spacings between energy levels decrease as n becomes larger. So what do I mean by that? So here's the spacing between n equals 1 and n equals 2. And here's the spacing between n equals 3 and n equals 4. Now, these aren't exactly to scale, but the point is that you go higher up in energies, these concentric rings get closer together. So if I had n equals 5, it might be right here. So closer together between n equals 5 and 4 than between 4 and 3. Next point. What is absorption? So if an atom absorbs energy, an electron can move to a higher energy level. And the process of moving to a higher energy level is referred to as absorption. So let's give an example here. So say I have an electron in its lowest energy level in the ground state, and it jumps up to n equals 2. Well, it jumps up because it absorbed energy. We could say that it's absorbing light energy. It's absorbing a photon. Anyway, that process is called absorption. If we look at before and after what this looks like, let's erase this. So we start here and we end here. Or on this diagram, we start here and we end here. And this is often depicted if we have, that's n equals 1, n equals 2. This change is often predicted just by an arrow indicating the before is the flat point of the arrow and the arrowhead is the end point of the arrow. And that process is absorption. Okay, so let's go to another example of absorption. Let's say again that we're starting before anything happens with an electron in the ground state. So here, ground state in n equals 1. And then we absorb a photon. So what's happening after? We absorb this photon that's a source of light energy, and you have enough energy to get up to n equals 4. So this is after. If you were depicting this by arrows, what this would look like, say on this diagram down here, is n equals 1 to n equals 4, and you could just use an arrow to do that. Or if you're using the circle diagram on top, here's n equals 1, n equals 2, n equals 3, n equals 4. Instead of a before and after, you could just show an arrow showing that transition. So, how do you compare the energies, the absorption transition energies? And the key is the larger the jump, the greater the absorption transition energy. So you're absorbing energy. So the higher energy the photon, we use photons as an example of the energy source. The higher energy the photon that's absorbed, the greater the jump. So in example one, we looked at going from n equals 1 to n equals 2. And in the second example, we looked at going from n equals 1 to n equals 4, shown here and here. And that the greater the jump, the higher the energy of that photon that was absorbed. So this requires a higher energy photon or higher energy to get there. Okay. There are ways, and it's in your textbook, where you can actually calculate those changes in energy. But if you just remember the basic picture of the Bohr model, you don't really need to calculate the energies. You can kind of look at the length of the arrow. So that's a small arrow, and that's a large arrow. So that means a larger amount of energy was absorbed. Next point. High energy states do not last long. So in the last two examples, we started at the ground state and we used energy to promote electrons to an excited state. And in the first example, we promoted to n equals 2, and the second example, we promoted to n equals 4. The, the time that that electron exists in a higher energy level is very fast. It's very short. It'll come down, it'll relax down, because objects naturally tend to lower potential energy. And just think of this example. Why lower potential energy? Say you have, some kind of rock on a hill. That rock really wants to roll down that hill where the potential energy is 0. Another example. Say you do some work and lift some keys. So keys were on the ground, and you do work to lift them up here, up in the air. Keys, I should say, at point 2 and keys at point 1. So you did work to get them there. But what if you let go of those keys? They're automatically going to fall back down, and that's because things tend to lower potential energy. The same is true for electrons. Excited states do not last long. They will jump back down to lower energy levels, and that's where they want to be. We haven't gotten here yet, but another reason is higher entropy, but that has nothing to do with this lesson. We're just looking at potential energy. Next point is, what is emission? When an electron in an atom drops from a higher energy level to a lower energy level, the process is called emission. So let's look at a before and after. Let's say that we previously, some point before this, had added energy to an H atom, and the electron, because of that, is in the n equals 3 level. N equals 3 level. And then, well, excited states don't last too long, and it's going to want to lower its potential energy. And so, say this in this instance, that it drops down to the n equals 2 level. So if we're drawing that in a circle diagram, we started off with n equals 3, and we're dropping down to n equals 2, and we could represent that with an arrow. And if we're using this type of diagram, where we have n equals 1, 2, 3, 4. If we're representing with an arrow, what this looks like is we're going from 3 to 2. Okay, let's do another example. So let's just say we have an electron beginning in the n equals 3 level again. N equals 3 on both of these. And then after this electron relaxes, it goes all the way to n equals 1. So here's after. If we're representing this with arrow, what this transition would look like is here we have 1, energy level 1, here 2, and 3. These are not to scale, of course, and the arrow would just look like that. And if we're using this type of diagram, 1, 2, 3, 4, the arrow would look like that. Okay, again, not to scale. Okay, so now I want to compare emission energies. So when these electrons drop down from higher energy levels to lower energy levels, they have to emit energy because energy is conserved. So let's just say this is emitting a photon. And I want to compare from example 1 and example 2 the energies of those photons. So how do I do that? So comparing emission transition energies, the larger the jump, the greater the emission transition energy, or the greater the energy of the photon that's emitted. And so in the first example, we were going from 3 to 2, depicted both here and here. In the second example, we were going from 3 to 1, depicted here and here. So which one is going to give off, get rid of that energy by a photon, the large amount of energy? And the answer is this one. The larger the jump, the more energy is given off. And without doing any calculations, though you can do calculations, they're given in your textbook, you can just look at the size of these arrows. So this arrow is much bigger than this arrow. And likewise, this arrow here is much bigger than this arrow, representing the magnitude of those energy differences. Now I just want to close out with doing an example problem. It says, which transition releases the higher energy photon? So this is an emission. And we're comparing an n equals 2 to n equals 4 transition. So here, n equals 2 to n equals 4. Versus n equals 3 to n equals 1. And well, we could look at arrow sizes. We could go to our textbook and calculate things. But just looking at arrow sizes, we see that this is the answer. And how would you always get this correct? Is just remembering that as you go further from the nucleus, the spacings get smaller and smaller. So this is a very large spacing. So n equals 1 to n equals 2 has a larger energy difference than, say, n equals 2 to n equals 3. And the spacing between n equals 3 and n equals 4 is smaller than the spacing between n equals 2 and 3. So they get closer and closer together. So we're kind of going n delta 2 here and delta 2 here. And since these are further apart, we know for sure that they're going to have a higher transition energy, so emit a photon of greater energy. I hope this was helpful. Thank you and have a great day.